Good afternoon, everyone. I am Zhijin, the first author of this work. Firstly, I would like to apologize that due to the visa problem, I cannot attend the conference and have to present our work through this video. Even though I still hope you can understand our work well. Okay, let's go back to the topic. A CNN cascade for quality enhancement of compressed depth images. This work will be introduced from 5 perspectives. Firstly, I would like to give a brief introduction about some related background. The next is the motivation of this work. Then the details of the proposed work will be given. After that, I will show you some experimental results, and at the end, I will conclude this work. Okay, let's move to the first part, background. Depth images are different from the RGB images that they use different grid levels to represent the distance between the captured objects and the camera. We could see from this figure, the darker areas mean they are further from the camera and vice versa. Texture images or RGB images associated with the depth images can provide users a depth perception of real things. That is to say, the scene looks more close to 3D scenario and more vivid than the scene obtained from traditional 2D images. At the same time, they can generate the content on the other viewpoints by some view synthesis techniques, for example, the depth image-based rendering (DIBR) technique. However, in comparison with 2D images, 3D images still put more pressure on the acquisition, storage, and the transmission units of multimedia systems. In this case, image compression schemes are demanded both for the texture and the depth images. As we know that lossy compression in general inevitably degrades the image's quality, especially for depth images, whose value represents 3D scene's geometric information. When encountered compression, severe geometric distortions, and virtual perceptual degradation over discontinuous regions will occur. This not only affects the quality of both depth image itself, but also the synthesized views in stereoscopic image applications. Here is one example. Before compression, the ground truth depth image is sharp at the edges, while the compressed depth is blurred. Therefore, the compressed depth generated virtual view suffers from wrong pixel location at edges. In order to avoid this visual perceptual degradation, the quality enhancement for compressed depth images is required. Motivated by the success of depth learning on object detection and classification, it also has been applied to low-level visual tasks. For example, the image super-resolution, image denoising, and compression artifacts reduction. On one hand, some of the deep learning-based depth enhancement methods require the assist from textures. However, it cannot always guarantee the aligned textures are accessible. On the other hand, some of the networks are designed with complex structures so that they have more training parameters, and the overfitting may occur if the training data is not sufficient. With these concerns, in this work, we propose a single input, single output, end-to-end fully convolutional neural network for quality enhancement of the compressed depth images. However, there are many choices for the network design. For example, we should adopt CNN, RNN, or other networks. We should adopt the AlexNet with only 5 layers, or the GoogleNet with 22 layers, or even go deeper, that use the ResNet with 152 layers. For the shallow network, it is easy to train with less data requirement. However, its performance is worse than the deep network. The deep network has its own weaknesses. For example, it is slow to converge and is data hungry. Inspired by the Three Gorges Water Conservancy project in China, where the whole dam is implemented in 5 levels, and the huge cargo ships are lifted from low water level to high water level, stage by stage. Hence, we propose a cascaded single input, single output, end-to-end CAN, and each cascaded unit is a 4-layer shallow network. Each unit can be treated as a pre-processing stage of the later one. Therefore, the image quality is enhanced stage by stage. Through cascading these shallow networks, we try to achieve a comparable results as the deep network. Here we list some details of the proposed network design. All the shallow networks are trained separately first and then cascaded to form a deep one. The size of a convolution filter for each layer is 9 times 9 times 64, 7 times 7 times 22, 1 times 1 times 16, and 5 times 5 times 1 respectively. Meanwhile, to avoid the spatial size decrease caused by convolution operation, we add 0 paddings for the layers whose kernel size is larger than 1. Parametric ReLU applied on the first 3 convolutional layers. After cascade, the whole network is retrained again. In this work, we propose to adopt weighted loss function rather than general loss function. Since the general loss function treats every part equally in the calculation, however, the edges in compressed depth images suffer more distortion than smooth areas and easily cause severe warping errors in synthesized views. The proposed loss function is shown in the slide, where AM is the weighted edge map, which is obtained from the Canon edge detection on the uncompressed depth images. In this experiment, small training samples, for example 22 times 22 instead of the whole images, are adopted to train the network. It has some benefits. Firstly, it takes much less time to complete the whole convolution operations and backpropagations. Secondly, it can generate more samples for training, so that it allows the network to come out with better results. 771,000 sub-images from the Middlebury 2014 dataset are used in the training process. Transfer learning is adopted that each cascade unit is trained on sufficient textures first, and then the learned weights are reused to initialize the network for depth images. Table 1 shows the quantitative comparison results with the state-of-the-art methods, and the PSNR gain can be up to 5.09 dB at quality 10 and 9.919 dB at quality 20 over the JPEG images. Moreover, this slide shows the virtual results of different methods. Since the proposed method can suppress compression artifacts on the depth images, it reduces the number of missing pixels on the synthesized images. In terms of the proper number of cascaded units, we find that it does not mean for the number of units, the more the better. The cascaded performance is saturated at some level. Over 95% PSNR gain is obtained from the first 2 cascaded units. Hence, we take two cascaded units, that 8-layer CNN, as our basic network by considering the computational efficiency and the memory cost. The effects of weighted loss function is shown in Table 2. There is a 0.23 dB and 1 dB gain respectively brought by the weighted loss function at JPEG quality 10 and 20 respectively. Okay, let me conclude this presentation. In this paper, a cascaded CNN is proposed to enhance quality of the compressed depth images. The proposed network adopts a weighted loss function which can emphasize the edges in depth images. In order to overcome the limited training data problem, the network is trained on textures first and then fine-tuned on the target depth images. Thanks for your time. And do you have any questions?